Hi, everyone. Hope you had a good lunch. Welcome to this session on questioning data and data bias. I'm Emily Wall from Emory University. I'm going to be chairing the session. So we have 6 great papers today. The first one is going to be virtual. The other 5 will be in person. The format is following 10 minutes presentation followed by 2 minutes of questions. So for the speakers, when you come up, feel free to remove your mask when you present if you want to. And be sure to engage with Discord afterwards. All of the potentially unanswered questions from Slido will be posted there. For the audience, make sure that you ask your questions by Slido, whether you're joining virtually or in person. That's where I will pull the questions from for the authors after. So we'll go ahead and kick off the first talk. This is a virtual presentation by Xiaolin Ron on vaccine, a visualization approach for noise awareness in quantum computing.
Hello everyone, thanks for attending this presentation. My name is Xiaolin Ruan, and I'm a PhD student at Singapore Management University. In this video, I will present our work, Vaccine, a visualization approach for noise awareness in quantum computing. This work is in collaboration with Yong Wang, Weiwen Jiang, Yin Mao, and Qiang Guan. The agenda of this presentation is as follows. In recent years, quantum computing has been proven a considerable speed up over classical computers. For example, Google demonstrated quantum supremacy using a 53-qubit quantum computer, where it spent 200 seconds to complete a random sampling task that would cost 10,000 years on the largest classical computer. Thus, quantum computing research has attracted considerable public attention and rapidly growing in past few years. Despite the promising speed up over the classical counterparts, the high noise level in quantum devices is one of the key challenges to achieving the real quantum advantages in today's quantum computers, which are well known as noisy intermediate-scale quantum computers. The reasons may be categorized as follows. First, the noise originates from quantum computers' fundamental components, the qubits and quantum gates, whose noise implicitly affects the accuracy of the results. Second, the quantum algorithm can be compared to various compared circuits with significantly different noise on the same quantum computer. For a large-scale quantum algorithm, the compared circuits can be several hundred. Due to the aforementioned issues, quantum computing users significantly suffer from the noisy execution. However, no tool that reveals the noise exists to assist the target users. Meanwhile, due to the rapid increase of quantum computing users, we face the increasing time of accessing cloud quantum computers without noise awareness. Thus, the evaluation and mitigation of noise before execution has become even more urgent to avoid the waste of queuing time for unsatisfied results. Currently, the common practice to obtain less noisy execution results is still a trial-and-error process. To bridge the research gap, we work closely with 5 quantum computing experts. Through a well-designed pilot study and iterative meetings for over 4 months, we summarized 5 design requirements, which are grouped into 2 categories: quantum computer selection and compared circuit selection. Quantum computer selection supports users to pick the appropriate quantum computer to execute the quantum circuits from a set of devices on the cloud quantum computing platform, which includes facilitating the temporal analysis of qubits and gate noise and making users aware of the latest quantum computing noise. For compared circuit selection, Vaccine allows users to select the optimal compared circuit regarding the various noises and usage times of qubits and quantum gates, which includes providing an overview of all compared circuits, enabling a detailed comparison of the usage of implemented qubits and gates, and supporting a real-time compilation and fidelity validation of quantum algorithms. Besides, experts also request flexible user interactions and intuitive visual designs. According to the design requirements, we proposed a visualization system for noise awareness during quantum circuit selection. The architecture of online visualization system is shown on the right. Vaccine consists of three modules: storage module, data processing module, and visualization module. The quantum noise of the execution results can be mitigated for quantum users through the interaction with the visualization system, which is intuitive and easy to understand for both novice and experts in quantum computing. However, several visualization challenges exist to bridge the research gap. First, it is challenging to temporarily visualize the complex noise factors as well as qubit topological connections along a timeline. To address this challenge, we propose a circuit-like design to portray the quantum computer noise in each time step. Through the design, target users can intuitively assess the overall performance of each quantum computers and their topological connection of qubits. Second, it is difficult to visually summarize a large number of compiled circuits regarding the various noises and enable users to select the most appropriate one shortly. To this end, we propose a coupled bar chart design, which supports an in-depth comparison of multiple compiled circuits. Thus, the users can be aware of the reliability of each compiled circuit regarding the performance and usage times of qubits and quantum gates. We first evaluate vaccine via two case studies on both small-scale and large-scale quantum circuits, a 2-qubit circuit and Shor's algorithm. We invite two domain experts from Case Western Reserve University and Fordham University to perform the quantum circuit execution based on our online visualization system. And now I will show you an example demo. First, the user uses vaccine to assess the noise in quantum computers in the computer evolution view. He can also switch between different noises, such as qubit error rate, qubit T1 time, and qubit T2 time. The gate noise can be revealed through the density area charts in the circuit-like design. Next, the user can choose the quantum algorithm to execute. After indicating the number of compilation times, the user can launch the compilation on the remote quantum computing platform. All compiled circuits will be returned to Vaccine for further assessment a few seconds later. Vaccine also supports flexible user interactions to inspect and filter compiled circuits. Once a compiled circuit has been selected, the corresponding detailed coupled bar chart will be shown in circuit comparison view. The user can compare them in terms of the qubit noise, quantum gate noise, and usage times. Once the user selects a compiled circuit for the final execution via the coupled bar charts, the circuit will be delivered to the quantum computing platform for execution. Then, the execution results and the corresponding fidelity will be shown in Vaccine. From the fidelity distribution, we could easily find that the fidelity of the selected compiled circuit has the highest fidelity among all compiled circuits. We further evaluate our approach via a well-designed user interview. We invited 12 participants from 6 different educational institutions and the National Research Library, Pacific Northwest National Library, to join our in-depth user interviews. Specifically, the participants were asked to accomplish the predefined tasks of selecting an appropriate quantum computer and optimal compiled circuit for execution. Finally, we also invited every participant to rate the vaccine system based on a 7-point Likert scale. The summarization of the results is shown in the slide. In conclusion, we present Vaccine, a visualization system to support real-time noise awareness in quantum computing. To inform the visual design, we identified 6 design requirements for visually analyzing a quantum computing specific problem. We proposed 2 novel quantum computing specific designs, a circuit-like design and a coupled bar chart design, to facilitate the temporal analysis of noise in quantum computers and in-depth comparison of compared circuits. We conducted case studies and in-depth user interviews with 12 target users to demonstrate the effectiveness of vaccine. The results show that vaccine can effectively make the users aware of various noises and further improve the reliability of the execution result of a given quantum circuit. That's all for the presentation of our paper. If you have any questions and suggestions, please feel free to contact me via the email. My homepage and the QR code are also shown below. Thanks for your attention. I'm open to any questions.
Okay, Xiaolin is joining us online to answer questions. There are a few in Slido already. As a reminder to the audience, go to Oklahoma Station 5 in Slido to post your questions. So the first one is about scalability of vaccine. So they're wondering if this can support additional qubits, for example, 128. Like, what do you anticipate as the scalability of your system?
Okay. Thanks for the question. Actually, it's a very good question. And our system may suffer from scalability issues when it is used to explore quantum computers with extreme numbers of qubits, let's say more than 100 qubits. And these issues may become more severe when the users are exploring the quantum computers in the view 1. But as far as we know, the general users can only access quantum computers with a small number of qubits, generally no more than 7 qubits, under the providers of the research hub in IBM-Q in most cases. So I think our system can work well in those common situations. Yeah.
Thank you. So one more quick question before we move on to the next talk. The next person is wondering if vaccine can be applied on other quantum computing platforms other than IBM.
Actually, we use IBM Quantum because it is, one of the most popular vendors in the world. Meanwhile, our approach can be easily extended to other platforms such as Rigetti, because the workflow and the dimension of noise data of quantum computers are similar across different platforms.
Okay, great. Let's thank Xiaolin once more.
Thank you. Thank you, Emily.
Okay, now let's welcome Tobias Eisenberg from NRIA presenting Do You Believe Your Social Media Data? A personal story on location data biases, errors, and plausibility, as well as their visualization.
Thank you. Thanks. So this is, as Emily said, a personal story on social media data, specifically carnivorous plant data, and ultimately also a story on the tragedy of my life. But more on that later. Let's start with the obvious. Carnivorous plants are cool. Not only the movie kind, but also the real kind. And there are people who like to see them in the wild, so they want to see the habitats where they grow. So let's use this example of this anonymous researcher here who's interested in the plants and look at this more closely. So he may have lived at different places and seen plants there. He may have traveled on vacation to other places, seen plants there, and maybe on some business trips and seen plants there as well. But now he moves to a new place and wants to know where to see the plants, right? So what does he do? Well, there's sites for that. You can search for data on locations, but usually you only find botanical gardens and stuff like that, so not really habitats. And the reason for that is clear, because most of these plants are protected and are endangered, and some of them on the red list, so people are afraid of poaching, so they don't post location data. So what can we do now? Give up? Of course not. This researcher looked at image sharing sites, Panoramio, which doesn't exist anymore, and Flickr specifically. And these sites not only share pictures, and descriptions for these pictures, but sometimes also geo-coordinates. So we can use data from these sites and try to extract locations. So we use the APIs, search for relevant images, and then we need to filter them. Because a lot of pictures there are not relevant. There's fake carnivorous plants, plants in botanical gardens, and plants at home, so we have to take these out. But then we end up with a data set with pictures, locations, and other data. And we presented a tool for looking at this data a couple years back at this, and that's cool, but here in this work, we're more interested in data errors and biases, and more specifically, geographic errors and biases. Of course, we know that GPS data is inherently imprecise, but are there other imprecisions in there? Did people, for example, move locations? And what other biases and errors are in the data? One error or bias is fairly clear immediately because the number of posts per person is heavily skewed. There's a power law distribution. Very few people are responsible for most of the images in the data set. And we can show that there's a power law distribution. The same is true for species. Few species get most of the attention, and again, we find the power law distribution. But what about geographic biases? And how can we analyze that even? Because we don't really have ground truth here, right? So what we did is we first looked for a baseline, some baseline that we can compare to. And for that, we use this Encyclopedia of Life. It's a group within Flickr that collects locations from geolocated images for species data. And this is all their data binned into different places on the planet. And first, let's remove all the lowest bin where the fewest number of pictures are in so that we really focus on where a lot of pictures are. And now we can compare that to our own data set that, of course, has a lot fewer entries. And we see that it's roughly similar. I'm just going to go back quickly, and you see that there's not that much difference. There are some, and I'll talk about this. But there are empty places on the planet, and why is that? So if you look at where people live on the planet and compare that to our data, then we see that there are places like these where lots of people live, but where we basically have no data. And that points to some cultural biases. Those people may not actually use services like Flickr. But then again, there's also other places where we have people living that are culturally very similar to people living nearby, but there's still a hole in the data. And that points to differences in habitat. There are certain habitats where these plants don't live. And if you then take both together, then you can explain, for example, differences in distribution maps between what botanists have established and what we find in our data, like for this plant. So here we see, like in Siberia, there's no data in our data set. But we can also look at a much smaller scale. So if you look at a very small scale, that we can see that people post pictures mostly where they can easily go to, roads and paths. So this is clearly another bias. But what about errors, intentional or unintentional? How do you find out about these because you don't have a ground truth? Well, the first thing that you can do is you can compare to other people's data. So for example, I can check for a given post, did some other person post on the same plant, same genus, or carnivorous plants at all nearby within a certain radius? And I have two examples here. And then I can mark these as same species is very good, same genus is still good. Any other carnivorous plants, similar habitat, also good, but if not, then I don't have proof that this could be believable. So we can find different kinds of evidence here. But we can also look at data from the same person, because if people post multiple pictures at the exact same locations, then this is an indication for an error. So if somebody posts just one image per day, then we can't say much about it, but if they post more pictures per day and don't put them all at the same location, so it means there's only one picture per a given location, then this is good. If there's two, then it's shaky. 3 or more is basically there has been some manipulation. But we can also use other forms of verification. So for example, we can check if there's plants where I knew before that there should be plants. So here the green are plants, sites that I knew about before. The white ones are from the data set. So this is an example from the Netherlands, which we could confirm. Another example from Canada, which we could also confirm. And then we can, of course, also use the data to go to new places and see if we can find plants. And this is one where I actually found plants. A butterwort here on the side, it's a little bit hard to see. And another example, also same as the previous one in Spain. There's also butterworts growing here. But there's also places where I went to check for plants and didn't find anything, and the habitat I saw was not plausible for the plants. So what happened here is a data imprecision. For that, let's look at one example a bit more closely, this one that I showed before. So in the center, we have the site that I confirmed, but then there's these other 3 sites that I didn't check, but that are nearby. And the cool thing is that we can look at these because we have picture data, right? So let's look at this one in particular, and here's the picture from that. And when I saw that, I was flabbergasted because I knew that picture because I had taken it myself. Here's that picture from my own visit, and here you see highlighted where that region is where the picture was taken. And the distance here is more than 5 kilometers. That's way beyond GPS imprecision. So this is not data imprecision, but this is data manipulation. And in fact, this is not just a random example, but this person who did that was responsible also for this mist trip, which was in Portugal. And in fact, this person was the 2nd largest contributor in our data set. So they actually posted a lot of pictures. And now, being a visualization researcher, what do? You look for patterns. So let's see if we can find patterns here. We plot this on the x-axis here. We want to put the images, the dates of the pictures, and also some other information, particularly the time in the day as well. So it's kind of 2 notions of time. So let's say the first picture in the day was taken here. And then I basically place any other picture of the same day within a certain distance, and this distance is essentially indicated by the logarithm of the distance traveled between the 2 pictures, right? And then I also encode with a color the speed that this person must have traveled at least between the 2 pictures, because I have timestamps and I have distances. If that's very small, like below 5K, walking speed, no problem. If it gets to 25K, I mean, a fast biker, maybe. If you have 80K, a car. If you have 200K, then whatever, a Ferrari. And beyond 200, you have to have an airplane to travel between these sites, right? And then you can color code this. There's also codes for no speed, so you stayed at the same location, and no time difference. And then you basically add more pictures in the day. And then for any additional days, you add more pictures. And we call this the motion plausibility profile. And here's that profile for the person I just talked about. And that shows some interesting patterns. So early in 2008, this person posted very few pictures per day and believable speeds. And then, around 2010 to 14, they posted pictures with all kinds of different speeds, including some where they must have had that fighter plane or something. And then after that time, essentially they decided that that was just too much work to manipulate all these locations and just posted every picture of a day at the very same location. So this motion plausibility profile essentially shows me that there is data manipulation going on. And this is where that previous example happened, and that's the other example. And we see that this makes sense now. So we also have a histogram of the data. There's some other examples of the motion plausibility profiles for other examples of the same data for other people, also other manipulation going on. And here there's also some manipulation of image place and time. And then we had a visiting researcher, and she destroyed everything because she told me, you know, the data that you collected was kind of futile because there's an app for that, which I didn't know. And then I looked at iNaturalist, which is a site that collects location data for species pictures for citizen scientists, and you can download data for all kinds of plants. And we did and looked at the same data. Also very interesting patterns, but usually we find more believable or more plausible data. We also compared the 2 data sets, again, find differences in culture. Some people use different tools in different places of the planet. There's a lot more data on errors and biases in the paper. I encourage you to look at that. To sum up a bit, I think we have to look with this kind of data beyond just uncertainty. There's also very interesting aspects about data errors, data biases, and data plausibility that we can try to visualize and draw inspiration from. Another aspect that I found quite interesting that is that data secrecy is kind of futile because you can figure things out still from this kind of data, as I saw in this data. There's a lot more information in the paper, extended materials. We have 2 versions of the paper. If you have color impairments, there's a version for you for that. We do not share our own data intentionally, but there's a GitHub repository for processing iNaturalist data. We got a GSI stamp for that, and all these images that I showed you from our own RCC BY. And then I promised you to talk about the tragedy of my life. Well, I live here, and yes, you can see there's no habitats nearby Paris. This is where the grandparents of my kids live, and again, there's nothing nearby. So that's the tragedy of my life. And finally, about the elephant in the room, what about Oklahoma? Well, worst conference location ever for carnivorous plants. But, you know, we should go to Florida, maybe. Anyway, that's it. Thanks a lot for your attention. I'm happy to answer questions.
Okay, thank you, Tobias, for this great talk. We have time for maybe one quick question. There's one from Alex Lex. Can you speculate why someone would manipulate the data instead of just removing geolocation?
Your specs, yes. This is actually very clear. The person I talked about, this example I showed, is a person who works in a botanical garden. And they are, of course, clearly interested in not sharing this precise location, but they share approximate location to indicate where plants live, approximately. I think the intention is to not allow you to poach the plants, but still know where they are, when that picture was taken, to not remove too much information. And I mean, from the post, you cannot identify where they got them from, but just roughly.
Great, let's thank our speaker once more. There are several more questions for you to engage with on Discord afterwards. So let's welcome our next speaker, Bhavya Gahe from Stony Brook, presenting D-Bias, a causality-based human-in-the-loop system for tackling algorithmic bias.
Hello everyone, I am Bhavya Ghai from Stony Brook University. In this presentation, I'll talk about D-Bias, a causality-based human-in-the-loop system for identifying and mitigating undesirable social biases from tabular datasets. This is a joint work with my advisor, Professor Klaus Müller. Let's look at what algorithmic bias is. So algorithmic bias occurs when computer systems discriminate based on protected attributes like nationality, like gender, etc. Real world has lots of biases based on race, gender, etc., which get encoded in different data sets. These biases are then picked up by machine learning models and which are then reflected in their outcomes, where machine learning models might treat different population groups differently based on their identity, which can be socially undesirable. Real world examples of algorithmic bias includes Compass, Amazon's recruitment algorithm, etc. The key takeaway here is that algorithmic bias is an imminent AI danger that impacts millions daily. In recent times, we have seen different media articles that highlight the different real-world examples of algorithmic bias. When it comes to the existing literature, there are a few tools that are aimed at tackling algorithmic bias. However, most of these tools are focused on detecting social biases and not mitigating them. So in this particular work, we are trying to fill in this gap. Let's look at D-Bias. So D-Bias is a visual interactive tool that embodies human-centered AI approach for bias detection and mitigation. In a typical ML pipeline, it operates over the raw data set, where we first try to audit for different biases and then try to generate the D-Bias data set. D-Bias relies on interactive causal models to present the underlying patterns in the data set, including social biases. These causal models also help incorporate the domain knowledge, which helps in the simulation of the D-Bias data set. This picture here shows the workflow of our tool. At step 1, we get the raw data set in, and we use a causal discovery algorithm to get the default causal model. However, this default causal model is not perfect because of the limitations of the causal discovery algorithm. So at step 2, we use some kind of human refining to get to the refined causal model. At step 3, we identify the undesirable causal relations and act on them and get the D-biased causal model. And at the last step, we try to simulate the debiased data set based on this debiased causal model. I'll go over each of these steps in more detail in the coming slides. Let's look at step 1, that is how to create the default causal model. So given a raw tabular data set as input, we use a popular causal discovery algorithm called the PC algorithm, which provides qualitative information about the presence or absence of causal relationships between different columns in the data set. This gives us a causal DAG, where each node represents a column in the data set, and each edge represents a causal relation. Next, we use something called as a structural equation model to estimate the strength of each of these causal relationships. Here, each node y is modeled as a linear function of its parent nodes. The strength of each causal relationship is encoded by the standardized regression coefficient shown here as betas. The larger the values of beta, stronger is the causal relationship. However, this default network might not be perfect and need human refining. Let's look at how this thing works in the interface. So the user first actually goes and selects the data set. Thereafter, they choose the outcome variable and then the set of categorical variables. In the end, they click on the causal model button, which triggers the PC algorithm and structural equation modeling on the backend, and we get something like a default causal model in the center of the interface. Coming to the refining of the causal model, so this picture on the left represents the causal model for the adult income data set. Here, the edges in orange represents the undirected edges. Debias supports a whole bunch of operations like directing, deleting, reversing edges for refining the causal model to get to the image on the right. So if we look at this in action, the user might select an edge and then choose any of these options from the top based on the requirement in that particular context to deal with all the undirected edges and all the wrongly or misidentified edges in this network to get to the refined causal model. Once we get here, we try to audit for different kinds of social biases. Debias supports 3 different ways to detect social biases. The first is the exploratory visual analysis, where Debias supports visualization of the underlying univariate and bivariate distributions to uncover sampling and historical biases. The second is fairness metrics, where Debias supports a diverse set of 5 fairness metrics. Lower values for all these metrics is desirable. And third is causal analysis, where Debias computes all paths from the sensitive attribute to the outcome variable to uncover possible direct and indirect discrimination. Now, if we see this in an example, let's say the user finds this, selects the source node as gender and the target node as job, and then click on the find paths button. This populates the set of paths that connects these 2 edges. On clicking on any of these paths, that paths get highlighted in the causal network view. Now, once we have identified the biases, let's talk about how to mitigate these biases. So for debiasing, a user first needs to identify the undesirable causal relations and then act on them by weakening or removing those causal edges. For example, in the case of adult income dataset, a user might find these 3 causal relations to be socially undesirable and might choose to delete these edges. This will give us the debiased causal model. Once we get the debiased causal model, the system will generate the debiased dataset based on the resulting causal model. The intuition here is that the dataset generated from the debiased causal model will be more fair. Let's now see how actually the debiased dataset is generated. Let's say in this example, the user chooses to remove the edge between the nodes S and Q. So the step 1 is to compute the set of nodes that are impacted by the user interaction. In this case, it will be the node Q and all of its descendant nodes, that is Y in this case. All other nodes are left untouched and simply copied from the original dataset to the debiased dataset, that is the nodes S, P, and R. At step 2, each impacted nodes, that is Q and Y, are generated using a weighted combination of its parent nodes, intercept term, and a random term. Here, the random term enhances fairness and minimizes data distortion. At step 3, we rescale the generated variables so that its distribution is close to the original distribution. Our approach overall focuses on minimizing distortion and enhancing fairness. For more technical details, we encourage you to see the paper. Now let's look at this in action again. So let's say the user finds the edge between gender and job to be socially undesirable. They might choose to weaken this edge by some percentage points, or they might also choose to remove this edge altogether, like in this particular case. The user can then assess the impact of their intervention by clicking on the Evaluate Metrics button. This computes a bunch of metrics. As we can see here, the utility metrics, that is F1 score and accuracy, are virtually unchanged. We see huge improvements in 5 different fairness metrics. There is a 2% data distortion caused by this intervention. And if you look at this four-fold display, the left half represents females, the right half represents males. So in the beginning, only 15% of females got the job, which got increased to 19% after this intervention. Similarly, 26% of males got the job, which now got to 25%. So originally, the difference between males and females was 11%, which came down to 6% in this particular case. Once the user is done with the debiasing, they can click on this debiased dataset button to download the debiased dataset, and then this new file can be used for any downstream application for more fairer predictions. Coming to evaluation, there are 2 different kinds of evaluation. For the ML-centric side of things, we have used metrics like accuracy, F1 score, to measure utility. We have used Goward distance to measure data distortion, and these 5 metrics for fairness. On the human-centric side, we have used things like trust, interpretability, accountability, usability, and cognitive workload. We tested our tool on the adult income dataset and the Compass dataset, but in the interest of time, I'll skip to the results section. In this table, we can see how our debiased dataset compared against the baseline. Here, baseline means the dataset without the sensitive attribute. As we can see, our debiased dataset incurs a bit of loss in terms of accuracy, and there has been some data distortion, but overall, it improves fairness significantly on all of these fairness metrics. So overall, we can say that debias enhances fairness, preserves accuracy for small data distortion. Coming to the human-centric evaluation, we conducted a within-subject study where each participant was shown the debias tool and the baseline tool in random order and asked to audit and debias a tabular dataset. Here, the baseline tool mimics the design of the debias tool, but has the workflow of an automated debiasing algorithm. And in the end, we measure metrics like usability, accountability, trust, etc. What we find is that debias outperforms the baseline tool in terms of interpretability, accountability, and trust. So if somebody is interested in these kind of measures, debias is the way to go. However, if somebody wants a quick solution and considers usability, maybe automated debiasing algorithm is more preferable. Okay, so in conclusion, we presented an end-to-end visual interactive tool for algorithmic bias identification and mitigation. We demonstrated effectiveness using 3 different data sets. In the user study, we showed how our approach outperforms on metrics like trust, interpretability, and accountability. One important thing here is that involving a human in the loop can be a double-edged sword, because if somebody chooses to ignore the social biases, then this tool becomes ineffective, or the user can even try to intentionally incorporate more bias by trying to strengthen the undesirable causal relations. In the future, we want to extend this approach towards word embeddings as well. And for more info, including the live demo, please see my webpage. With that, I am open to any questions. Thank you so much for your attention.
Great. Thank you, Bhavya, for a great talk. We have several questions in Slido. The first one is from Alex Endert, who says, in your before and after comparisons, do you have experience with how well people are able to tell if the resulting causal network is less biased?
Okay, so in terms of the causal network, what we are looking for is the causal relations and their strength. So as I said, if a causal relation is like the underlying data generating mechanism for the debiased data set. So if there is no undesirable causal relation, it means that the debiased data will also have no undesirable patterns. Or if there is a lesser strength in the causal relation, there might be lesser impact of, let's say, the sensitive attribute gender or race in the outcome data set.
Thanks. So one more quick question. Does it make sense to set your desired model outputs and then see how these can be achieved through the modeling?
I think you can do that. There are a lot of like machine learning papers that try to do those kind of things. But again, we were focusing here on things like trust, interpretability, accountability, etc. For that, you need to have a real transparent interactive system. Doing that via an optimization algorithm might not achieve these, might not perform well on those human-centric metrics.
Great. Let's thank our speaker once more. Okay, our next talk is going to be presented by Sanmu Ha from Washington University on a unified comparison of user modeling techniques for information relevance and exploration bias.
Thank you, Emily. Hello, my name is Samuha. I'm part of the Visual Data Analysis Group at WashU, and today I'm happy to present our work. So capturing and analyzing a user's interactions is integral to research and visual analytics, as they contain a lot of information about the user and their data interests. Many in our field have leveraged machine learning techniques to decode the information embedded in the user's interaction log data to intelligently assist the user during data exploration. And this general goal of understanding the user and their sense-making process is called user modeling. So there has been a significant progress in developing user modeling techniques, but a unified comparison of these proposed techniques is lacking on different data sets, tasks, and analytic scenarios. So comparing these techniques is not as of a simple task, as some of them are presented theoretically, others are validated with a controlled user study or with a single data set, and algorithms are not standardized or readily available for use. So to address this, we performed a computational benchmark study to compare user modeling methods to proposed in the visual analytics literature using publicly available user interaction log datasets. Since work on analyzing user interactions is diverse, we want to narrow the scope to real-time algorithms that learn from interactions with data points. Such user modeling techniques fall under two categories: data interaction prediction and exploration bias detection. And here, data interaction prediction is when you infer which data points the user will likely explore next or in the future. And exploration bias detection is when we detect whether the user is biased towards more certain attributes in the data. So how do we choose which models to compare? Our selection process started off by reviewing papers that covered user modeling techniques from 2010 to 2021 in major journals and proceedings in the Viz and Chi communities, HCI communities, and this resulted in a corpus of 110 manuscripts, and we narrowed this pool down to the final selection of 7 papers based on our scope. All 7 are real-time algorithms for data interaction prediction or exploration bias detection that are either freely available, have precise pseudocode, or can be successfully implemented with a reasonable amount of troubleshooting and debugging. So our main contribution is a comparison and evaluation of the performance of these 7 user modeling algorithms, along with an ensemble model with 4 publicly available interaction logs from user study experiments with visualization systems. The ensemble model is a collection of our 7 selected models, which combines the predictions of all the techniques that predict data interactions and all of the techniques that detect exploration bias. So we'll first look at data interaction prediction. To evaluate data interaction prediction, we incorporated a probabilistic output for each model during the implementation process that predicts the next data interaction. This means that the model treats every data point on the visualization as a potential candidate for being the most relevant to the user's data interest. And as the models observe the user's interactions, the data points are ranked based on the model's beliefs. The model then reports the top K data points for K equals 1, 5, 20, 10, 20, 50, and 100. So let's look at the best case scenario with one user study data set, St. Louis crimes. This data was collected by Otley et al., and it includes directed tasks with little exploration noise. We're going to focus on one single task that a participant answered. This is a type-based task because the task elicits the participant to focus on only one single type of crime, homicide. They were asked to, out of all the cases of homicide, one case differs from other cases with regards to time. What is the time of that case? So how did the models do on predicting the next interaction? This chart shows the average success rate of the data being within each model's prediction set for varying prediction set sizes. Most of the techniques for the can predict the next data interaction point with a high success at K equals 100, which represents 5% of the underlying data. We can observe that the ensemble model is outperforming all of the other models. We then move on to a more analytic scenario where the task is more open-ended. So this data was collected by Wall et al., and it provided users with a set of 180 fictitious politicians and asked users to select a committee of 10 candidates of their choice to review public opinion in Georgia. The users had access to a variety of features from each politician, such as gender, age, policy views, and more. And here we can see the task is less direct and more open-ended. We use this data to stress test the modeling techniques and observe their performance on a set of minimal but intentional interactions. At k equals 100, competing models, which is here highlighted in orange, and analytic focus, highlighted in green, showed the best performance. So what do we learn from data interaction prediction? We presented the best and worst case observational scenarios for user modeling. From the results, we gathered a few insights. The models performed well when the tasks are very highly specific and the data contains little to no noise. But when the task is more open-ended, we see a drop in performance. In most cases, there is an improved performance with data interaction prediction with the ensemble model, but we do note that this can be costly and might not be suitable for real-time systems. The paper includes additional results, and I encourage you all to refer to the paper for more detailed evaluations. Next, we'll move on to expiration bias detection. On the other hand, evaluating expiration bias detection is not as simple as data interaction prediction, as their access to ground truth is not always available. With the previous directed user study that I mentioned, we can use the task as the ground truth bias. For example, count the number of aggravated assaults in the red shaded region. We know that the bias should be assaults in a certain location in the red shaded region. However, with open-ended studies, the ground truth bias is not so clear, as users can exhibit their own set of biases as they explore the data. And in order to evaluate exploration bias detection for open-ended user studies, we had to manually code for bias. Going back to the political committee data that we mentioned earlier, we performed a qualitative coding on each study participant's interactions to determine if there was an evidence of bias. The manual coding was performed by comparing each participant's interaction distribution, which is highlighted in orange, to the full data distribution. The plot on the right shows participant lemma's interaction density plots against the full data set. We found no significant distribution for all the attributes, which was a pattern that was similar for the rest of the 11 participants in the data set. So here we see density plots juxtaposed with each algorithm. For expiration bias, this plot shows each algorithm's belief of bias for a participant lemma as they interacted with the data visualization. And although our qualitative coding revealed no significant differences between the distribution of values explored by lemma and the underlying distribution, the models presented false positive bias, often with high certainty, which is indicated by the opacity of the squares on the plot. So the main insight was that we observed exploration bias detection, that even in the case where there is no evidence of bias in the user's explorations, the models presented false positives. Interestingly, some of the models that can detect exploration bias have underlying assumptions that the user is always biased towards data attributes. There are definitely pros and cons to this approach, as false positives could potentially erode the user's trust in the algorithms, especially in proposed applications related to assisting the user to recognize their own exploration bias or recommender systems. I'll end this presentation with a few takeaways. Our work shows that there's no clear winner among these 7 user modeling algorithms, and the right algorithm depends on the tasks. Additionally, implementing an ensemble model provides a good solution. We need to improve the detection of bias detection algorithms, as many of them make assumptions that may not hold true in real-world scenarios, and that could question the practicality of the technique outside of academia. To advance the research in user modeling, we need to standardize how we implement algorithms and make the code for the techniques readily available for others to use. Lastly, we need to continue the trend having user study data sets available so that others can utilize the data to further evaluate their techniques. You can find our implementations, pre-processed data files, and links to the manuscripts used in the study on our GitHub repository. And I would like to take my time to thank my collaborators and my advisor, Dr. Alvida Otley, for their guidance and assistance in this project. I am open to any questions.
Thank you, Sunwoo, for the excellent talk. I just want to quickly remind the audience that you can use Oklahoma Station 5 and Slido to ask any questions. We have one to start, which is, apart from trust, can you speculate about some of the potential benefits and trade-offs of using less than perfect models, and specifically ones that have these high false positive rates?
So I think that as in the visual analytics scenario, we might not, when we explore data, I should be talking to Mike, sorry. When we're exploring data, we may come into the task not knowing what to find, and so having that flexibility and maybe potentially having that sort of false positives could potentially guide the user as well to maybe think about some things that they were not having bias towards.
Great, thank you so much. Let's give Sunwoo another hand. Okay, while I'm juggling laptop and microphone. Let's welcome our next speaker, Cindy Zhang, on seeing what you believe or believing what you see, belief biases correlation estimation.
All right, hi everyone, I'm Cindy. I'm here to share with you all how our belief can influence how we look at scatter plots. And this work is done with some really wonderful collaborators, Chase Stokes from UC Berkeley, Yeso Kim from UW-Madison, and Stephen Francaneri from Northwestern. So imagine you just collected some data, and you decided to plot the data points on a scatter plot, and this is what you see. So you draw a mental regression line through your data and realize that the correlation isn't very high. And then you remember that this data was actually depicting the relationship between air quality and the number of environmental regulations. You've had experience in this area, and you firmly believe that there exists a positive correlation between the two. So you take a closer look at your scatter plot and convince yourself that something must be wrong with these two outlier points. You discount their presence and draw another mental regression line through the rest of your data points, and now the correlation looks a lot stronger. And it makes much more sense to you given your existing belief on how they should be related. So when we conduct an experiment to ask, to what extent does this happen in visual analysis? And specifically, we ask two questions. The first, do people make different correlation estimations depending on the context? And by context, I mean whether the scatter plot you're looking at is labeled with something that's abstract, like X and Y, or something that's more real world, so like air quality and number of environmental regulations. And second, are people's estimation of correlation strength associated with their beliefs? So to answer these questions, we conducted a series of experiments. To kind of walk you through how it works, I'm going to plot time from left to right. We showed participants scatter plots like these, labeled with X and Y, and at a later time, we showed them the exact same scatter plot, but now labeled with these real-world variables, and we added a distractor task in the middle so they hopefully don't remember exactly what they see. And they were asked to estimate the correlation that they see in this scatter plot. And for example, they could estimate 0.6 for one of them and 0.7 for one of them. And we tested a series of different topics, including number of trees in the neighborhood and number of people whose names begin with a T, and they did the same thing. And in addition to these scenarios where the correlation is not super plausible, we also made sure to cover scenarios where the topic is more belief triggering, like the air quality and regulations one, but also maybe crimes and number of gun ownership in the community. And to make sure everyone is on the same page when they enter our experiments, we gave them a pre-training on how to read scatter plots and how to estimate correlations. And another thing is that in addition to creating these conditions where the topics are either not plausible or belief triggering, we also made sure to actually ask people for their beliefs on these topics at the very end of the study. So for the belief elicitation component at the end, we asked them to rate on a scale from 1 to 7, how much do you agree with a following statement? And that statement is a statement that describes a potential relationship between real-world variable pairs. Like, I believe the number of people whose names begin with T's in the neighborhood increases, the number of trees in that neighborhood increases. And we do that for all the conditions that we tested. So let's look at some results. Just to quickly remind you, we wanted to know if people made differing correlation estimations depending on the context. So what I'm going to do is I'm going to compare their estimation in the XY label version to the real world label version. I'm going to plot the correlation estimation that people did on this chart and to walk you through some hypothetical scenarios to begin thinking about how to interpret the data I'm about to show you. So I'm going to just give you some examples. So pretend these two circles are data, but if the data looks like this, it means that people, the real world variable pairs make people overestimate the correlation. If the data were to look like this, it means that the real world variable pairs make people underestimate the correlation. And if the data were to look like that, that means there's no difference between the two. Okay? All right, so here's what the data actually looks like. And we see that on average, real-world variable labels make people underestimate the correlation. So I would like to answer yes to this question. People do make different correlation estimations depending on the context. However, before I can confidently say yes, I like to rule out some potential confounds that may be triggering, causing this effect that we're observing. And that is, it could just be the passage of time or just seeing the same scatter plot multiple times that's driving this difference between people's estimations. So we conducted a control scenario of this same experiment. Everything is kept the same, except that in the second component after the distractor task, we showed them the same exact scatter plot again, but labeled with X and Y rather than throwing any real-world variable labels in there. And here's some data on that. And you see in the control version on the bottom, there is no difference between the two kind of phases before and after the distractor task, whereas when in the original version, when you do add the real-world variable labels, the second phase, you do see a very significant difference between how people made their correlation estimations. And we can move these guys up to allow some kind of between condition comparisons. And you do see that among the X and Y labels, there is indeed no difference. But once, again, you add in the real world variable labels to a scatter plot, people's estimation of the correlation really begin to change. So this allows us to rule out these confounds and more confidently say, yes, people seem to be making different correlation estimates when they see scatter plots labeled with real world variable pairs. And now let's take a look at question 2, which is, are people's estimation of correlation strength associated with their beliefs? And just a quick reminder, we did ask them to report their beliefs on the relationship on a scale from 1 to 7. So here on the x-axis, I have that scale for you from 1 to 7. And this is what the data looks like. And we see here, they seem to underestimate the correlation for the real-world variable pairs when they don't believe that those two variables should be correlated. And they overestimate that when they do believe, or more strongly believe, that relationship to exist and to be correlated. And we can directly visualize the difference between the two. And so basically the box plot over here on the bottom is just taking the orange and subtracting the purple, taking the XY label and subtracting the real world variable label, and you see it, the difference is distributed over a box plot. And the red horizontal line shows the median. And so the conclusion here is to say the stronger the belief, the more likely people will overestimate correlations when they see these real-world labeled scatter plots. And so to answer question 2, yes, it seems like strength of belief does impact the way people make correlation estimates. And now you may be wondering, could this effect be driven by the fact that we elicit people's belief at the very end of the experiments after we've already shown them some visualizations? So in a way, maybe their belief is kind of primed by having seen some visualizations in the experiment. So we also did another version where we asked for their belief at the very beginning of the experiment before they've seen any hypothetical data or just real-world variable pairs, and this is what the data looks like. And you can see that we observe the same pattern. Doesn't matter if we are eliciting their prior belief or their posterior belief. So this belief-driven over and underestimation seems to be predicted by both the prior and the posterior belief. And I'm adding some comparisons so you can see how similar they look. So just to quickly conclude, people's correlation estimation is associated with their beliefs, and what we're observing, it seems like the stronger the belief, the more likely people will overestimate their correlations, and vice versa. So imagine you have some data depicting a 0.5 correlation, just to give you a feel of what the effect size that we observed in our experiment is. If you have a hypothesis going into it to see a strong correlation, you're going to overestimate the strength of that correlation. But on the other hand, if you don't believe a correlation should be strong or a strong correlation should exist, you're going to underestimate that correlation. Okay, so while we're still trying to figure out why this happens, I'm going to offer you some potential speculations, food for thought. So imagine looking at this scatter plot. You could convince yourself that some data points are indeed outliers, and then you can choose to discount them, right? Or when people read scatter plots, they could be perceiving the correlation between the two variables with some uncertainty. And depending on what your beliefs are, you're going to choose to report on either range of that uncertainty to either over or underestimate it. And it is also very possible that when people look at scatter plots that have real-world variable labels, they just choose to not look at the real-world variable labels and let their belief drive their conclusion. So we're hoping to follow up on these possible mechanisms and the goal is to, through understanding how people understand data and how they may be biased, we can potentially design mitigation tools or interventions to help people be less biased when they do visual analysis. And that is all I have. I'd like to thank my very lovely collaborators, and thank you all for listening to me.
Okay, thank you, Cindy, for an excellent talk. We have several questions in Slido. The first one is, does people's expertise affect how they make correlation decisions?
That is a really good question. So when you mention expertise, there's two types of expertise, right? Expertise with the domain and also expertise with just reading visualization in general. So what we did is we added these additional factors, we call them demographic factors, that asked for their visual literacy or for their familiarity on a topic, but we actually observed no effect of any of them. So no effect of, we even tried political orientation just for fun. There's just nothing, right? So we didn't observe any significant effect of that. So I would say this may be generalized and it may be exacerbated by these additional factors, but it seems pretty generalizable.
Thank you. The next question is, how do you think the findings would be different if the order was changed to show the real-world label first, then the distractor, then the abstract?
Yeah, really good question. I thought I did enough conditions to cover all possible cases, and you managed to throw me another one at the conference. Thank you for the question. I don't know, but I would imagine because priming seems to be an effect after seeing one instance of something, just even if it's something really not plausible, people seem to believe it a little bit more. I would imagine just because after seeing it, it's on your mind, so the difference between the two estimations, the XY and the real-world variable pair, if the order were switched, would be slightly smaller. That's my speculation. But again, I think either way, you would still observe a pretty significant belief-driven effect.
Okay, I'll quickly ask one more because it was also upvoted a couple times. Did you measure which is more accurate, with or without the real-world label, assuming that you know the exact correlation value?
Yeah, a really good question. So we know from previous work in like just perceptual psychology and just scatter plot perception that people are pretty good at estimating correlations. And what we did is we compared our data. Didn't make it into the paper. We compared our data with their data, and then people are pretty good when they're estimating the XY variable correlation, and they get them biased by their belief when they see these real-world variations, and then they become less accurate.
Great. Let's thank our speaker once more.
Thank you.
Okay, and then wrapping up this session with one more final talk, an exciting one on data hunches, incorporating personal knowledge into visualizations by Han Lin at University of Utah.
Hi, my name is Han Lin. Today I'll be presenting our work, Data Hunches, incorporating personal knowledge into visualizations. Hopefully you're not bored with COVID data. I'm going to show it again. So let's start with this New York Times visualization on COVID cases in Utah. For 2021 holiday season, they denoted data anomaly. However, that was not the case for 2020 holiday season. In this chart, we see that there are 2 dips in case counts near Thanksgiving and Christmas. However, based on our understanding of how COVID data is collected, this is likely due to reporting agency not reporting during the holiday season, probably not an actual dip in case numbers. And we have seen similar things in our lab work with domain experts. However, in our work Sanguine, we designed and implemented a visualization interface for analyzing transfusion data in hospital settings. When we presented the interface to surgeons, they had doubts about data that the visualization showed. So the visualization showed them low blood recycling usage. However, based on their experience, they will always turn on the machine for blood recycling. Hence, they suspect that these were missing charting when the volume of blood recycling was low. Another work done in our group recorded similar encounter. When we designed a visualization application for experts studying Zika outbreaks, we noticed that different experts have knowledge about the imperfections of the Zika case reporting. For example, one country only reports cases in Zika in pregnant women detected within their first trimester. Another country reports all confirmed cases and suspected cases as confirmed cases. Or one country just don't report any cases because their union goes on strike often. These knowledge are implicit when the experts are viewing at the visualization, yet they heavily impact on how they interpret the visualization and the data behind. And our visualization were ineffective to explicitly show the personal knowledge or to be used to communicate the knowledge to others. These are just 2 examples that we have reported in publications, but we have seen many similar cases in our collaboration and conversations with domain experts. Experts that know about their data, they know a lot about their data, and that knowledge is not known to us, the visualization designers. So we want to first put a name on this, and we arrive at the term data hunch. In this work, we formalized the term data hunch to describe the knowledge that uncertainty isn't quite enough for. So we define data hunch as the analyst's knowledge about how and why the data is an imperfect and partial representation of the phenomena of interest. Data hunches have been prevalent and important, but often implicit, and it impacts how data is perceived and is as important as data when it comes to describing the phenomena of interest. We want to formalize data hunches so that we can emphasize the important role that personal knowledge plays in data analysis. With us putting a term on to actually describe this knowledge, we can start to think how we can explicitly record and communicate data hunches in visualizations. And with our design exploration, analysts can use our proposed techniques to communicate their data hunches with their colleagues. So before we dive into how our techniques are, let's see how they're actually communicated right now. For example, again, another COVID data. So New York Times denoting that many states did not report any data on Memorial Day, so as an annotation. There are lab notebooks that recorded data caveats, which often get translated into method sections in a paper to communicate these data caveats. Or we just only verbally communicating them, or even just not even talk about them at all. So these existing methods provide very limited ability to externalize data hunches explicitly. And it is hard to communicate and share them effectively and intuitively. With all the rich research we've been doing in interactive data visualizations, we think we can do a lot better when it comes to record data hunches. So we begin to brainstorm how can we explicitly show data hunches in an intuitive way with visualizations. So we think that data hunches can be recorded in any charts. For example, in a line chart where a user can draw their data hunch, in a network, adding a node and edges, or indicating that an edge should be removed, or in a bar chart indicating a different value should be higher than the original visualization, or in a map where the user can express a different categorical color filling. But different charts can vary in difficulty when implementing data hunches in it. So for our work, we decided to focus on bar charts. To show how data hunches can be recorded and communicated, we built a prototype where a user can record data hunches with the techniques we proposed in our paper. Before I dive into the prototype, let's quickly step through what kind of data hunches can be recorded. To start with the assessment hunch, it speaks to the quality or trustworthiness of the data set. For example, a user may give a high rating as they consider the data collection trustworthy. There is value hunches. A user may think the reality of France COVID cases is between 700 and 1,400 based on their knowledge about France collecting COVID cases data, or that New Zealand might have COVID cases around 3,000 instead of 2,800. And finally, structural hunches speak to the inclusion and exclusion of data items. For example, a user would want to exclude not applicable in this data set about CS student research areas and add that to the unknown category. So we can see how data hunches can be recorded in our prototype. We have a bar chart with student research area distribution in an institution. One faculty reviewed the distribution and made the comment. Database is classified as data and visualization, but I think in my institution it should be under computer systems. So with our prototype, they can actually record this value hunch in the chart. And then they also see that robotics looks smaller than what I think it should be. Maybe some students got classified as AI incorrectly. So they can record a range for students in robotics based on their data hunch and adjust the AI areas accordingly. After reviewing the student distribution and recording their data hunch, they show their recordings to a fellow faculty. To review a data hunch, they can see the reasoning behind the data hunch by hovering on it and upvote if they agree with the data hunch. And here it is. We have recordings of data hunches in the visualization, and now they can pass the visualization with the data hunches to other faculties to review. From our literature research and iterative design process for the prototype, we generalized our lesson learned into these guidelines for designing for data hunches. When considering other techniques that we didn't mention or didn't implement, the techniques should still fulfill for most of the design principles. I'll go through a few here since time is limited. First off is never changing original data. Techniques for data hunches are used to express knowledge about the data, not a tool to alter the data set. Data hunches is another layer of information added on top, and there should be a clear difference between data and data hunches to avoid confusion and to retain the integrity of the original data. And second is make data hunch distinct, and this is consistent with do not change data. Data hunches should be clearly distinguishable in the visualization and give the intuition that this is clearly not the same as the original visualizations. In our prototype, we opt for sketchy rendering hand drawing fonts to distinguish them from the original visualization. Also using sketchiness, also emphasize the human factor in data hunches. But at the same time, make data hunches similar. This is in terms of the visual encodings. Similar visual encodings can help with comparison with the original data. It makes reading data hunches a lot easier without the need for mental conversions. Reasoning and context is critical to support the validity of data hunch. Therefore, in our prototype, we require all data hunches to be accompanied with reasoning so that a reader can understand the data hunch fully. We also recommend recording author identity to establish trust. We hope to open new design opportunities by recognizing data hunches and proposing techniques to record them. but there are some issues and ethical considerations that we need to address. We identify 3 main challenges and concerns that come along with data hunches, and we have detailed discussion on them in our paper, and I will only go into the first point here. Does data hunch reinforce user biases? Ideally, we think that data hunches can provide rich knowledge to understand the data and reality, and that all parties involved should be positively contributing based on their knowledge and understanding. However, there is a possibility that data hunch is being used to explain away inconvenient data point or to reinforce an analyst's preconceived ideas. We think that requiring explanation and justification can help other readers to evaluate the data hunches holistically, but this remains an open question to be investigated. So now what? This is only the first step to formally recognize how much personal knowledge plays in interpreting visualizations, and we only explore the tip of the iceberg. There are many more techniques that we can explore to record data hunches. As we recognize the role of personal knowledge in general data interpretations, we wonder how can we bring data hunches into a variety of visualizations and contexts, or how about we try data hunches in design studies? And second, we as a community should recognize and value the role of personal knowledge in data analysis. Here, our paper formalized the personal knowledge with data hunches and explore the design opportunities, but that's only the first step. It can be challenging, but our community should start considering how to incorporate data hunches in analysis tools and designs. You can find more about data hunches on our website here through the QR code, and thank you for listening.
Thank you, Hyon, for a great talk. There's a couple questions in Slido. The first is, how did you come up with the taxonomy for types of data hunches?
We went through quite extensive brainstorming just to see what type of data hunches are being really recorded, can be recorded. So we went through our past design studies with domain experts and see like what type of knowledge they had about the data, and then we try to make them into those types in our paper. So mostly just brainstorming and try to generalize it to cover most of the cases. Yeah.
Great. We'll do one more quick question. What are your thoughts on encoding agreement or disagreement as part of the visual marks when other colleagues verify or refute a hunch?
I'm sorry, the later part?
So it's about when you have multiple people who may verify or refute a hunch. What are your thoughts on encoding whether there's agreement or disagreement between multiple data hunches?
So there, of course, there can be like disagreement with different data hunches because it's, after all, personal knowledge about the data. And right now, we only have like upvotes and downvotes on data hunch, and it's just a way to show that you can have collaboration aspect with data hunches. But for a future work, we definitely want to incorporate something like comment sections where you can leave more extensive thoughts about like hunches, and then having disagreeing data hunches can also just show how much personal knowledge really plays into how we look at data.
Great, thank you so much. So now we have a coffee break until 3:45. Feel free to come up and engage with the speakers further about the really great talks that they gave. And then once more, let's just thank our tech support, the student volunteers, and all the speakers in this session.